Good morning, everyone. In today's session, we are going to discuss about the characteristics of the d block elements. In the previous lectures, we have already discussed about the characteristics of the s and p block elements. The position of the d block element, as you can see in the periodic table, the position of the d block element is in between the s block element, which are present towards the left hand side, and the p block element, which are present towards the right hand side. So that's the position of the d block element. So we will discuss here only about the d block element characteristics. So let's start today's session. So what are the main characteristics of the d block elements? The main characteristic of the d block elements include their definition. So what are the d block elements? The d block elements are those elements. Before explaining about the definition of the d block element, first of all, we must have to write down the electronic configuration of one of the element. The first element of the d block is the scandium, atomic number 21. You can write the configuration of the d block element: 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2, like that. So here is the diagram. You can see there's the nucleus, that is the 3d, that is the anti-penultimate d subshell, the valence 4s subshell. The valence 4s subshell, there are the two electron, and the last electron here enters into the penultimate d subshell. So on that basis, by seeing the electronic configuration, by seeing that diagram, now we can write properly the definition of the d block elements, where that last electron going to enter, whether that last electron enters into the valence shell or the penultimate subshell. So you can see here the last electron here enters into the penultimate d subshell. What is the penultimate? The last shell is called as a valence. Valence word is used for the last one, and the penultimate is used for last but one, means second last. Means for the second last shell or the subshell, we can use the word that is the penultimate. Here the position of the 3D subshell in case of the scandium here is the penultimate one, means the 3D subshell is present at the last but one position, at the second last position, because the last one here is the 4s subshell. So on that basis, you can see here the last electron enters into the penultimate d subshell. So the proper definition of the d block element is the elements, all the elements in which the last electron enters into the penultimate d subshell are called as the d block elements. And the first element of the d block element is scandium. So the conjugation of the scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s2. As we all know, the configuration of the calcium, that is the element just before the scandium, whose atomic number is 20. What is the configuration of the calcium is 1s2, 2s2, 2p6, 3s2, 3p6, and the 4s2, means 4s2, means 4s already filled up to the element that is the calcium. So then after calcium, whose atomic number is 21, the next one is the 20, whose atomic number is the 20, calcium 20. The next element, that is the 21, that is the scandium, where the next electron will enter. The next electron will enter into the 3D subshell. And after entering the electron into the 3D subshell, the 3D will come back in their original position, that is in the third shell. Third shell area is 3s, 3p, and the 3d. And now the valence one is the 4s. Valence is the 4s. Fine. So that is the definition of the d block elements. The d block element, what is the position of these d block element? The d block elements are present from group number 3 to group number 12. So that is the range of the 3D block elements, group number 3 to group number 12. As you can see in the diagram here, there are total 18 groups and the 7 period. Of these total 18 groups, the first group and the second group belongs to the S block, and the group number 13 to group number 18, that belongs to the P block elements. Now the remaining groups, that is the group number 3 to group number 12, these belongs to the D block, and these are 10 in number. These are the 10 in number. Why 10? You can see in the diagram above, D subshell has 5 orbitals. And these 5 orbitals can have a maximum of 10 electrons, 2 in each orbital. So as there can be a maximum of 10 electron in the d subshell, so the maximum number of groups for the d block will be the 10, and that ranges from group number 3 to group number 12. So that is the answer of that particular question, why the d block has 10 groups. In the starting of the d block elements from the period number 4th, where the first d block element, that is the scandium, present, the first d block element is present in the 4th period. That's why the last you can see in the configuration of the scandium 1s2 2s2 2p6 3s2 3p6 3d1 and 4s2, the last shell is shell number 4s, that is the last one, because that scandium belongs to 4th period. So during the discussion about what is the period, you just see the last shell, maximum last shell. So last shell is 4th shell, so it is a 4th period element. So the first element is scandium. So d block element starting from the scandium, atomic number 21. So in the first series of d block, that ranges from scandium 21 to zinc 30. These are the 10 elements, and you can learn them like that. SC Sachin, TI Tendulkar, very CR cricketer. Sachin Tendulkar, very good cricketer. Mange, MN means Mange. Fico, FECO, Fico. Niku, NICU, Niku Jan. Mange, Fico, Niku Jan. So that is the way you can learn that first series of d block element that ranges from scandium atomic number 21 to zinc atomic number 30, and these all elements are: first scandium, second Ti titanium, third V vanadium, whose atomic number is 23, scandium 21, titanium 22, vanadium 23, chromium 24, manganese 25, iron 26, and the cobalt 27, nickel 28, copper 29, and last in that particular series, that is a zinc atomic number 30. In the next d block element series, which starting from Y ytterbium and ends at cadmium 48, right? So these are the total 10 elements in that particular series also. Here is the one particular element, that is the technetium, atomic number 43. That is the synthetic element. All other are the natural element here. That only the synthetic element. There is a separate book on the technetium also, synthetic elements book, in which there is a complete description about that element, that is a technetium. So ytterbium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, and the cadmium. These all 10 elements belongs to the next series of the d block. As we all know, when you write the configuration of the d block element, like the scandium here, in the scandium you can write the configuration like that: 1s2 2s2 2p6 3s2 3p6 3d1 4s2. But there is a common thing. You can see here in the scandium that d subshell is not the fulfilled one. There is one electron in the d subshell, one electron. That one unpaired electron is here. On that basis, there is a new term comes here in the d block element chapter, that is the transition elements here. Transition element, on the basis of the definition, we can say transition element are those elements in which d subshell is partially filled. D subshell is partially filled either in neutral state or in ionic state. In the neutral state or in the ionic state, you have to learn that definition of the transition elements. How will you define the term transition element? The elements in which the d subshell is partially filled either in neutral state or in ionic state. You can see in the scandium, in the neutral state, the d subshell is partially filled, right? And in ionic state, after losing these two electron, there is also the one unpaired electron in the scandium. If scandium shows +2 oxidation state, because these valence 2 electron can be lost easily. So there is one unpaired electron. So it is the transition element. So to watch whether a particular element is a transition element or not, what we can do, just see that element in both state. In neutral state, it must have unpaired electron. If there is no unpaired electron, no way. Then see that element in their ionic state. In ionic state, if there is something unpaired electron, then it is also a transition element. So in that way, we can see about all these element, all these d block element, which of the following are transition element, which of the following are not the transition element. Means these all are d block elements. Scandium to zinc, these all are d block element. The ytterbium to cadmium, these all are d block elements, but all are not the transition element. Means all D block elements are not transition elements, because in all these D block elements there is something, there is one or two or three or more means elements in which the D subshell is not partially filled. D subshell is fully filled in both ionic and the neutral state. For example, you can see here the zinc. How can we directly write the configuration? There is a simple trick, simple way to learn the configuration of any of the element. For example, in scandium, you can say atomic number is 21. You just simply see the valence configuration is 3d14s2. Why 3d1? 3d11. I am saying here 1 because the atomic number is 21. There is 1. In titanium, what is the configuration? Atomic number 22. 22 last में 2 है, तो just write 3d24s2. Other inner configuration will remain same. Vanadium 23, just write 3d34s2. Chromium, just write 3d44s2, but there is an exceptional case here. In case of the chromium, when you write 3d44s2, one of the 4s electron comes back in the 3d to make it half-filled configuration, 3d54s1. That's the exception one for the chromium. Okay, so next one is the manganese 25. In the last there is 5, so 3d54s2. In cobalt there is 27 atomic number, 27 in the last there is 7, so 3d74s2. In nickel 28, 3d84s2. In copper 29 atomic number, 3d94s2. So again the exceptional case, one of the 4s electron comes back in the 3d and the conjugation of copper becomes 3d10-4s1. That's the due to the fulfilled D configuration, fulfilled D subshell. In the zinc, you can see here 3d10-4s2, 3d10-4s2 in case of the zinc. So D subshell is fully filled in case of zinc, right? So as the D subshell is fully filled in the neutral state, so it is not the transition element according to the definition of the transition element. So see the zinc in the neutral, in the ionic state. Zinc shows only one oxidation state, that is the +2. Means these two, after losing these 2 electrons, zinc comes in the +2 oxidation state. Although you can see the D is fulfilled. D is fulfilled even after the losing 2 electrons. So zinc is not the transition element. Why zinc is not the transition element? Because according to the definition of the transition element, the element in which the D subshell is partially filled, not the full filled, either in the neutral state. In the neutral state of zinc, D is fulfilled, 3d10. In the ionic state, after losing 2 electrons, 3d is fulfilled. Means D subshell is fulfilled in both neutral and the ionic state in case of the zinc. So zinc is not the transition element. It is the D block element, but not the transition element, right? Next, we can see about the copper, whose atomic number is 29, exceptional configuration. 3d9-4s2, 1 electron comes back, means 3d10-4s1 is the configuration of the copper. 3d10-4s1 is the configuration of the copper. So when you see the configuration, that is the 3d10-4s1. So what you will see here means 3d10 means after losing 1 electron, copper shows 2 oxidation state. One is the +1, means after losing that, means I tell you here the configuration of the copper is 3d10-4s1. After losing 1 electron, that from the 4s1, conjugation is 3d10, means that is the fulfilled. That means copper should not be the transition element. But in another oxidation state, means copper shows 2 oxidation state, +1 and +2. When the copper loses 2 electron, the conjugation becomes 3d9, means now the D subshell is partially filled. So the copper is the transition element. So that's the definition of the transition element. The elements in which the d subshell is partially filled either in the neutral state or in ionic state. So on that basis, in the first series, we have only 9 transition elements. The last one, that zinc, is not the transition element. That type of question may be asked in your examination. You must have to learn such type of questions. In the next series, so that the first transition series element, scandium to zinc, that is the first transition series element. The second transition series element ranges from ytterbium to cadmium, So in that particular case, there is one more exception relative to the electronic configuration. Palladium, in case of palladium, you can see here the what is the way of learning the conjugation? Just increase one shell. In the first transition series element, the configuration is valence configuration is 3d14s2. In the second ytterbium to that one means what is the configuration for the ytterbium? Below that is present below the scandium. So as the configuration of scandium is 3d14s2, so the configuration of ytterbium is 4d15s2. Just increase one number in the valence area. So which I shown here in the red color. So the in place of 3d14s2, just write 4d15s2 for the ytterbium. Just increase and so on throughout the series. So on that basis, what is the configuration of palladium? The configuration of palladium will be, because the atomic number of palladium is 46, that is present below the nickel. So what is the configuration of nickel is 3d84s2. So the configuration of palladium is 4d85s2. So in case of palladium, that's the special case, the 4s both electron comes back in the, these two electron comes back in the d. So the configuration of palladium becomes 4d10 5s0. So there is one element in the d block element whose configuration can be written like that. So the general configuration हम आगे देखेंगे. So the general configuration of the d block element is from n-1 d 1 to 10 and ns 0 to 2. Why we write here n-1 d 1 to 10? Because the electrons are filled in the d subshell, means in scandium there is d1, in titanium d2, vanadium d3, chromium d5 due to exceptional case, manganese d5, in iron d6, cobalt d7, nickel d8, copper again d9 की बजाय d10 due to the exceptional configuration, and the zinc d10. So means the element are ranging between 1 to 10. So we write here in the general configuration n-1 d 1 to 10. Why we write here ns 0 to 2? In case of, you can see, in case of the palladium, both the s electron jump back into the d subshell. So the configuration becomes 4d10 and 5s0 in case of the palladium. So 0 in case of palladium. So 0 here. Why the 1? 0 to 2, we write here 0 to 2. 1 in case of that chromium, where the configuration is 3d5 4s1, and in case of below chromium, that is molybdenum, the same case here. So you can write like that. Okay. And in case of copper also 3d10 4s1, and same configuration in case of the silver, which is present below the copper, that is the copper, silver and gold. All the three have the same type of configuration, that is the 1 electron in case of the s, valence s. So the general configuration for the d block element is n-1 d 1 to 10 and ns 0 to 2. So you can understand now better, in the better way. I have already explained all these way why the configuration of the d block element is n-1 d 1 to 10 and ns 0 to 2. So that's the way. Now the next characteristic is the d block element can show the variable oxidation state, because in the d subshell the electrons are not present in the same number. In case of scandium, you have already seen the number of electron in the d subshell is 1 and the valence for s is 2. So the common oxidation state is +2 because they can easily lose these valence for s electrons. So the common oxidation state in all the d block element is +2. That's the common, means all the element can lose 2 electron easily, because the in the valence shell, that is the s subshell, here the number of electron present here are 2, so they can be lost easily. So the common oxidation state of the d block element is +2, because in all the d block elements, the 2 electron are present in their valence shell, so which can be lost easily. So the common oxidation state is +2. You will write the answer in that way after writing the configuration. Whenever that question is asked, what is the common oxidation state of d block element, you will write the +2. For reasoning, you must have to write electronic configuration of 1, 2, 3 elements, which shows that there are the 2 electron in their valence shell, which can be lost easily. So you must have to give an example to explain that common oxidation state +2. Okay. Or to explain why they show the variable oxidation state, you have to write the configuration of first element, that is scandium. You can write one more element and the last one also, like that of the zinc. So by writing these configuration, you can easily explain why they show the variable oxidation state. So means very simple answer, there is very less energy gap in between the 3D and the 4s. The proper answer why the d block elements show the variable oxidation state. Now the proper answer is due to very less energy gap. Due to the very less energy gap in between the 3D and 4s, means due to nearly the same energy, or you can say you can write like that, due to nearly the same energy of 3D subshell and the 4s subshell. Due to nearly the same energy of 3D and the 4s, the 3D electron can be lost like that of the 4s. जैसे 4s के इलेक्ट्रॉन इजीली लॉस हो सकते हैं, वैसे ही 3D के भी इजीली लॉस हो जाते हैं, because the energy of 3D and 4s is nearly the same. So the element can show +2 oxidation state, along with after the loss of that 3D 1 electron in case of the scandium, it can show one more oxidation, that is the +3 oxidation state. So scandium shows these 2 oxidation state, that is a +2 and +3. Scandium is not showing only one oxidation state, that is +2. It's showing 2 oxidation state, that is a +2 and +3. Why that showing +3 also? As I already explained, the energy of the 3D is nearly same that of the 4s. So the 3D electron can be lost like that of the 4s. So it can show the +3 oxidation state along with the +2. Means the d block element can show the variable oxidation state, and the explanation can be given like that. You can see the diagram here. What is the definition? Here the definition of d block element in the diagram, the last electron entering into the penultimate d subshell. So that is the d block element definition. And you can see here the diagram for the scandium. 1 electron is present in the 3D and 2 electron present in the 4s. These 3D electron can be lost like that of the 4s, so they can show the variable oxidation state. As there are 2 electron in the valence shell which can be lost more easily, so the common oxidation state is +2. Among all these d block element, you will see these 4s2 electrons. So after that, the next series in the d block, after the first and the second series elements, the first series ranging from scandium to zinc, the second series ranging from ytterbium to cadmium, the next element in the periodic table which is present just below the ytterbium is the lanthanum, whose atomic number is 57, lanthanum. But the next element after the lanthanum is hafnium, that is the atomic number 72. Where the other 14 elements? These 14 elements are placed at the bottom of the periodic table in the horizontal form, that is the atomic number 58 to 71, that called lanthanides, that is the F block elements. Because in these elements, the last electron enters into the anti-penultimate F subshell. We will discuss about the characteristic of the F block element in the next lecture. But as we are discussing about the D block elements, so that's why I'm talking about where these elements gone. So these elements are placed at the bottom of the periodic table, atomic number element having atomic number 58 to 71. So the next element of the third transition series element after the lanthanum is hafnium, that is the atomic number 72. After that, tantalum, tungsten, you heard about the name of the tungsten? Tungsten filament, bulk filament, rhenium, osmium, iridium, platinum, gold, and the silver, that is the liquid metal here. So these are the element of the third transition series. So you can see the first transition series, scandium to zinc, second transition series, ytterbium to cadmium, third transition series, lanthanum to mercury. So that's the third transition series. After that, you can see the next element, that is the below, that is present below lanthanum, that is the actinium, atomic number 89. But the next element is rutherfordium, whose atomic number is 104. Where other element gone? So atomic number 90 to 103. That's the another one series which is present, the previous series at the bottom of the periodic table, whose atomic number ranging from 90 to 103. That also the F block element, because in these element also the last electron enters into the anti-penultimate F subshell. So these two series, that the F block series, which are present separately at the bottom of the periodic table. So that about the D block element series. But one more interesting thing here, we must have to learn about something else. That is these three elements you can see here: iron, cobalt, nickel. These collectively called as the ferrous metal. These collectively called as the ferrous metal, and the element whose characteristics, whose properties are major one, that the iron one, so called, these are the ferrous metal. Next, the sixth element that is present just below the iron, cobalt, nickel, that present just below the ferrous metal. These six elements: ruthenium, rhodium, palladium, and osmium, iridium, platinum, these collectively called as the platinum metal, because the dominating element properties are of platinum one. So you have to learn in exam, if the examiner asks what are the platinum metals, so platinum metals are 6 in number. These are ruthenium, rhodium, palladium. These are the ruthenium, rhodium, palladium, and osmium, iridium, platinum. These six collectively called as the platinum metals. What are the coinage metal? These three elements in group number 11. These previous element, that is the ferrous metal, they are ranging from group number 8 to 10. In the group number 8 to 10, iron, cobalt, nickel, and similarly in the same group number 8 to 10, these platinum metals are present. That may be asked in your examination. Now, what is the position of coinage metal? These coinage metal, they are present in group number 11 of the periodic table. That is the copper, silver, gold. In the previous time, in the ancient time, the coins are formed from these precious elements, that is the copper, silver, and gold. So they called as the coinage metals. The last group number 12, zinc, cadmium, and mercury, these are present. So that about these all element, in all the element configuration, there are 2 electron in their valence S subshell, which can be lost easily. So these all element common oxidation state, whether the D block element belongs to first transition series, second, third, and so on, all element have the common oxidation state of +2. The region will remain the same, because in all these D block element, the valence shell is the S subshell, and the electron present in them is 2, which can be lost easily. So the common oxidation state is +2, right? The next property, that is the catalytic property. These D block element, all the D block element has large surface area. All the D block element has unpaired electrons in there. D subshell, we can see in scandium there is D1, D2, and so on. So due to the presence of large surface area, due to the presence of unpaired electron, they can provide the surface area for the incoming reactant molecule to come and sit on their surface, and thus they provide and they alter the pathway of the reaction and thus speed up the rate of the reaction. As the D block element provide the surface area for the fresh reactant molecule to come on and sit on their surface, and thus they come closer to each other and they collide with each other, and thus they increase the rate of the reaction due to that particular surface area. So that nature and these D block element remain unaffected even after the completion of the reaction. There occurs no change in the nature of that particular substance. So the substance which remain unconsumed even at the end of the reaction, which increase the rate of the reaction, which alters the rate of the reaction, such type of substance is called as the catalyst. Means the D block element shows the catalytic properties. They show the catalytic properties. So that question may be asked in your exam, why the d block element act as the catalyst? Due to the large surface area, due to the presence of the unpaired electron, they provide the surface area for the reactant molecule to come and sit on their surface, and thus they changes the pathway of the reaction and increase the rate of the reaction. So they act as the catalyst. You can write like that. You can see in the diagram also here. That is the surface area of the catalyst, platinum catalyst here. Here the molecule like the oxygen molecule, they come and sit on the surface. The carbon monoxide molecule come on the surface, and then now they collide with each other, result in the formation of the CO2. So otherwise, the molecule are moving randomly because oxygen is a gas, carbon monoxide is a gas. In of the absence of that catalyst, that the solid catalyst which provide the surface area, these molecules are moving randomly in the container from one place to another, and there is very less chances for the collision between them, and thus the very less chances for the formation of the CO2 gas. So that's the region here. The platinum act as the catalyst because it provides the surface area for these gases molecule to come and sit on their surface and result in the formation of the final product. Next property means they act as the alloy. They can form the alloy. They can form the alloy. Why they can form the alloy? What is the meaning of the alloy? Alloy is a homogeneous mixture of two or more metals, two or more elements. If we have the homogeneous mixture of two or more elements, that is the alloy. How that homogeneous mixture can be formed? Means if we place, you can see here, a crystal lattice of one of the element, one of the d block element, we can replace, now you can see we can replace one of the element like copper is replaced. For example, that's the lattice of the copper. So one of the copper atom is replaced by the, for example, zinc, and so on and so on and so on. And thus that from the brass, copper 60% in that lattice. If the copper is 60% and zinc is 40%, that is called the brass. You call it as a brass, and that brass is used in utensil, cartridge caps, means brass is used there. Next one is the bronze. If that is the crystal lattice of the copper, and these blues atom here are the tin, it means if the composition the crystal lattice is 90% and the 10%, 90% copper and 10% tin, that is the bronze. You already listen about that bronze medal. Okay, so these bronze can be used in control valves and the statues also. So that is about the alloy. Means due to nearly the same size, we will explain why the d block element of the particular series have the nearly the same size. So due to nearly the same size of these d block elements, they can occupy the position of each other. डी ब्लॉक जो एलिमेंट होते हैं, उनके जो एटम होते हैं, उनके नियरली सेम साइज होते हैं, इसलिए वो एक दूसरे की पोजीशन को ऑक्युपाई कर सकते हैं, वो एक दूसरे को इजीली रिप्लेस कर सकते हैं क्योंकि उनका साइज नियरली सेम है. वी विल गिव द रीजन ऑफ दैट व्हाई दे हैव नियरली द सेम साइज. You can see here on moving from scandium to zinc, in the whole series from left to right, in all the element, the valence shell is 4s. Valence shell is 4s. So, and the number of electron will also the same on moving from scandium to zinc, that is 4s2. So as the number of shell remains the same, number of electron in the valence shell remain the same. So the attraction between the nucleus and the valence shell is almost nearly the same, or due to almost nearly the same interaction between the nucleus and the valence 4s subshell, the size is almost remain the same. So because of that region, the from the first transition series element have almost nearly the same size. There is something change in the size. We will explain later on. But the demand here about that particular point means the d block element can form the alloy. Demand is only that how can we explain why that first transition series element have nearly the same size. I have explained only that here, why the d block element of the first transition series almost have the same size. So the proper reason is because in all the element ranging from scandium 21 to zinc 30, all the element have number of shell remain the same. The last shell is 4s. The number of electron in the 4s remain the same. So due to that reason, the attraction between the nucleus and the valence shell almost remains same. So the size is almost remain the same. We will write like that in the examination. So because of that reason, because these d block element have nearly the same size, so they can easily replace replace the atom of each other in their crystal lattice, so they can form the alloy. The next property is the d block element can form the interstitial compound. Why the d block element can form the interstitial compound? What is the meaning of that interstitial sites? Interstitial site means these small spaces which are present in between the atom in their crystal lattice. In the crystal lattice, after the arrangement of these atoms, you can already hear that or study in the chapter of solid state. One of the atom is assumed as a sphere. We show here all atom in the form of the sphere in the spherical shape. So when these all atom are placed in a proper manner, so that there must be the very less gap between these atoms, that possible way is that called the close packing here. After the close packing, there is also a very small gap between these atoms, and that is called the interstitial sites or the void. The other name of the void is interstitial sites. And in these interstitial sites, the small size atom, you can see, I have shown here with the blue color small size atom like the carbon, nitrogen, hydrogen. These small size atom can be placed easily, can easily be fit in these interstitial sites, and the compound after placing the small size atom in the crystal lattice of d block element, that called the interstitial compound. When you place the small size atom, hydrogen, carbon, nitrogen in the interstitial site of the d block elements, the compound finally formed called the interstitial compounds. So why the d block element can form the interstitial compounds? What is the reason behind that? You will simply write that the small size atom like carbon, nitrogen, hydrogen, they can easily be fit in the interstitial sites which are present in the crystal lattice of the d block element, and thus they can form the interstitial compound. You will write like that. You can see. Next property, next characteristic of the d block element means they can form the colored complexes. Why they can form the colored complexes? Colored complexes formation means release of the energy by these compound or the atom in the visible region. So how can we explain that the energy going to be released in the visible region? In what way? First of all, we have to write the electronic conjugation. As we have write here the electron conjugation of the scandium. In the scandium, you can see the valence conjugation is 3d14s2. And in the ionic state of the scandium, means scandium 2 plus state, means there will be only one electron in the d, that is the 3d1. So that d electron, you can see if the compound is present in aqueous state, या moistness state, in presence of magnetic field or the electric field. We have heard that in the polar medium, like in the moistness or in the magnetic field or in the electric field, these all the 5 orbitals of the d subshell, which are here you can see all present in the same line, means all are degenerate, all have the same energy. In below diagram you can see that is the energy line, and these all the 5 d orbitals are present in the same energy level, means all are degenerate orbitals. But in presence of polar medium, in the presence of magnetic field, or in the presence of electric field, these d subshell 5 orbital no longer be degenerate, means all the 5 d orbitals no longer have the same energy. They split in 2 sets depending upon the nature of the complexes, whether the complex is the octahedral complexes or the tetrahedral complexes, which we will study later on. Means octa means when the central metal atom is surrounded by the 6 ligands, means metal atom forms the 6 bond around them by the different ligands which are present around them. That the octahedral means. Tetrahedral means the central metal atom forms the 4 bond with the surrounding ligands, surrounding species, you can say. That's the tetrahedral one. So means when we have the octahedral complex, means metal atom is surrounded by the 6 surrounding species which are going to form the bond with the metal atom. So in that particular case, the d subshell orbitals, d subshell split in 2 sets. In that way, the 3 d orbitals are present below these 5 1 and 2 above 1, means they split in two sets, and these two sets called as the T2g and the EG orbitals. T2g and the EG, the below one are the dxy, dyz and the dxz, and the above one are dx square minus y square and the dz square. So that's the splitting in that way on the basis of their shapes that we will discuss in the chapter of the d block elements. Okay, so you can see here in case and the energy gap is something depending upon the number of the surrounding species. If the surrounding species are lesser in number, the gap is lesser one. If the surrounding species are more in number, the gap will be more. As we are discussing here, octahedral or the tetrahedral complexes, in octahedral there are 6 surrounding ligands, so the gap will be more in between T2G and EG. And if there are tetrahedral complexes, the gap will be something less, because in tetrahedral there are the 4 incoming ligands, 4 surrounding ligands. So that is the simple way for showing that when the gap between these two sets, that is a T2G and EG, will be more or the less, that depending upon the number of the incoming ligands, number of the surrounding ligands which are present or which are surrounding the metal atom. Okay, so main question here is, okay, how can we explain the d block element or their compound from the colored complexes? How can we explain how the energy is going to release in the visible region? So as we already discussed about any of the compound which is colored, how can we explain that? We must have an electron, unpaired electron, which must move from lower energy level to higher energy level. So that can only be possible in case of the d block element, when that d subshell orbitals, these degenerate d subshell orbitals, split in two set. Now we have the two energy levels, that 2t, T2g, that is the lower energy level set, and the EG, that is something higher energy level set. Means now we have the two energy gaps. There is an energy gap, but we have the two set of different energy level. Means now when we feel, for example, D4 configuration. D4 configuration is of scandium, titanium, vanadium, chromium. But in case of chromium also, we have D5 configuration. That is an assumption. Okay, if we have the D4 configuration after losing electron in a particular oxidation state, if we have D4 configuration, so means D subshell has these 4 electron, and in polar medium, these D subshell split in two set. And where these electrons are present, 1, 2, 3, and 4. Now they are present like that. And now how can we explain that there may occur something movement of the electron? Means one of the, after absorbing the energy from the surrounding, the one of the T2 electron, one of the, you can see here, one of the T2 electron move into the EG. Means transition of the electron takes place. From where? From one D set to another D set. One D set here is T2G, another D set here is the EG. Means there occurs a DD transition. And when that, after absorbing energy, one of the D electron jump into the another D set orbitals after absorbing energy and become unstable. Now that electron become unstable. When that unstable electron comes back in the ground state, releases the energy in the visible region. So the d block element or the d block compound are colored. They form the colored complexes. But the condition here is, as we already explained here, the d block element which have the unpaired electron, there must be an unpaired electron, first condition. Second condition, there must be a polar medium or the magnetic field or the electric field, so that we have these two set of the d subshell, that is a T2G or the EG, or in case of tetrahedral, reversal takes place, that is the E at the lower energy state and T2 at the higher energy state. So due to the DD transition, in simple way you have learned in your books, due to the DD transition, the d block elements are colored. So what is meaning of that DD transition? Means the transition or the movement of the electron from one D set to another D set after absorbing energy, and comes back from one D set to another D set after losing energy, and after losing that energy in the visible region. So d block element or their compound from the colored complexes. You will explain like that. Okay, you must have to take one example during the explanation of that question, why d block element from the colored complexes. Okay, now the next property of the d block element, next characteristic of the d block element, they can form the coordination compound. As we already explained in the previous point, d block element surrounded by the ligands. So that's the way here you can see that is the d block element, or in a neutral state or in the ionic state. Now the d block element have these vacant d orbital. Now there is the ligand. Ligand means electron rich species which have the lone pair electron to donate their electron. Means here is the one is the acceptor, the one is the donor. Donor acceptor means coordinate bond is going to form. So these compound called the coordination compounds, because these compounds are bulkier one. These are the large size one. They are also called as the complexes. The coordination compounds are also called as the complexes here, because complex compound, simple compound, these are large size compounds, so called the complex compound. They are the coordination compound. Coordination compounds are the compound in which a coordinate bond is found between the ligands and the metal atom. Vacant orbital are present in the metal atom or the metal ion, and the lone pair electrons are present on the ligands. So due to formation of that coordinate bond, the coordination compounds are formed. So the metal atom has vacant d orbital, so they can accept the electron pair from the incoming ligands, and thus they can form the coordination compound. So reasoning is that. Okay. Now the next characteristic, they are generally paramagnetic in nature. They are paramagnetic in nature. We have already explained. For example, in case of scandium, there is one unpaired electron, so that is paramagnetic nature. The substance which have unpaired electron in their shell or the subshell, they called as the paramagnetic in nature. So the way, how can we find whether a particular element is paramagnetic in neutral state or the ionic state? Just write down their electronic configuration. In neutral state, if examiner is asking about their ionic state, for example, if examiner asks, tell scandium is paramagnetic or not, you will say the scandium is paramagnetic in nature due to the presence of one unpaired electron in 3D. Now the examiner asks why, tell whether scandium +3 is paramagnetic in nature or not. Scandium in +2 state, when you lose these 4 s2 electrons, there is also 3d1, means one unpaired electron. So scandium in +2 state is paramagnetic nature. But if examiner asks about their +3 oxidation state, what you will say? After losing these 2 4s electron and 1 3d electron, there is no unpaired electron now available in the 3d subshell. So it is diamagnetic in nature. So it is not paramagnetic in nature. So before giving a response to any of the question during your examination, you just write down the electronic configuration of any of the element about which the examination is going to ask about their magnetic nature, whether it is the paramagnetic or the diamagnetic one. Just write down the electron configuration in their neutral state first of all, and then remove the electron after writing the neutral state. Never write the configuration directly in the ionic state. That may give you the wrong response, wrong answer. First of all, about any of the element, first of all, always write the configuration of that element in their neutral state. For example, here the scandium, we have write the configuration in their neutral state. After that, examiner is asking about +1 oxidation state, just remove one electron. That one electron will be removed from 4s and not from the 3d. Because here the valence shell is 4s, not the 3d. You just have to see here. So the configuration of +1 is 3d1 4s1. Okay, that's the configuration of scandium +1. Scandium +2, remove 2 electrons from the valence 4s. The configuration is 3d1 4s0. Okay, so you have to write, you have to observe like that, and then give your response in your examination. Next property after the paramagnetic nature is, means you can explain all the paramagnetic nature of all the element like that. Just write down the configuration and find and see their configuration, whether the unpaired electron is present or not. You simply see the paramagnetic nature. On moving from scandium to zinc, just see. In scandium, one electron is present in 3d1. Scandium d1, one unpaired electron, paramagnetic. Titanium 22, d2, paramagnetic. Vanadium 23 atomic number, D3, 3 unpaired electrons. Chromium 24, exceptional case, 1 4s electron jumps back into the 3d, means 5 unpaired electrons in case of the chromium, 3d 5 4s1, total 6 unpaired electron, means paramagnetic in nature. After that, in manganese, 5 unpaired electron, 1 2 3 4 5, 3d5 4s2, means 5 unpaired electrons. In chromium, 6 unpaired electrons. The maximum unpaired electron in chromium. In manganese, 5 unpaired electron. After that, in case of the iron, the configuration is 3d6, because 26 last में 6 है, so 3d6 means 1 2 3 4 5 and 6, means Hund's rule apply कर दिया आपने. After applying Hund's rule, which states that how you will fill the 6 electron, Among the degenerate orbital, because all the 5 orbitals of d subshell are degenerate, means same energy, means among the degenerate orbitals of the p, d or the f, first of all electrons are filled up singly, then pairing will takes place. So for the iron, how will you fill these 6 electron 3d6? 1, 2, 3, 4, 5 and 6, means pairing of the electron takes place. Means after the manganese, the pairing of the electron takes place. Means on moving from scandium to zinc, initially the number of unpaired electron increases up to the chromium, means 6 unpaired electron, then 5 in case of, and after that the pairing of the electron takes place. You can see in case of the iron, there are the 6 electron, means one pairing state place. In cobalt, 27, 1, 2, 3, 4, 5, 6 and 7. Now the 7 electrons, means 3 unpaired electron remaining, means the pairing of the electron takes place. You can explain the pairing of the electron takes place. So in that way you can explain about the paramagnetic nature. You can see the number of electron initially increase up to the middle, and then number of unpaired electron decreases due to the pairing of the electron. Similarly, the paramagnetic nature initially increases up to the middle, and then due to the increase in the number of unpaired electron, after that pairing of the electron takes place, so the paramagnetic nature decreases. So in that way you can explain the paramagnetic nature of the d block elements. Means d block element are paramagnetic in nature, and you can also explain their paramagnetic nature on moving from left to right or in that way. Next property is the high melting or the boiling point. Means the formation of the bond depend upon the number of unpaired electron. In the previous case, in the previous point, we have already explained the number of unpaired electron. The number of unpaired electron increases up to the middle, means on moving from scandium to chromium, 6 unpaired, manganese 5 unpaired electron. Then the pairing of electron takes place, means number of unpaired electron decreases. So means the number of intermetallic bond, the bond which are going to be formed between the atoms, that is the intermetallic bond, metal and metal के बीच में जो bond बनेंगे, the number of intermetallic bond increases up to the middle because the number of unpaired electron increases. So number of intermetallic bond increases. Number of intermetallic bond increases means more energy is required to break these intermetallic bond, to melt that particular substance. So melting point also increases. So means d block elements have high melting point and the high boiling point, and we can also explain the trend of that melting point. Means melting point increases up to the middle and then decreases, and lowest melting point is of zinc because there is no unpaired electron. Fine. So you can explain about the melting point and the trend of melting point. They are hard metal. In the similar way, the number of unpaired electron moving from scandium to zinc initially increases up to the middle, means number of intermetallic bond increases. So the hardness increases because the hardness means the interaction between the metal and metal. Interaction between the metal and metal depends upon how many number of bonds are going to be formed between these metal. Means on moving from scandium to zinc up to the middle, the number of unpaired electron increases. So number of intermetallic bond increases, so hardness increases. After the middle, the number of unpaired electron decreases, so number of intermetallic bond decreases. So the number of intermetallic bond decreases, so the hardness decreases. So the zinc is a soft metal. Zinc is a soft metal. It is soft. Or you can see in the third transition series, the mercury is liquid one. It is so soft that it is not the solid, it is liquid. Okay. That's the next point. Next characteristic of the d block elements. They can form both ionic and the covalent compounds. Means they can lose the electron. They can form the covalent bond by sharing the electron. So they can form both type of compound, that is the ionic and the covalent compounds. They are malleable and ductile because of their metallic nature. They are malleable, they are ductile, as we already explained during the determination of the characteristic of the S or the P block element. We have already discussed these two terms, that the malleability means conversion into sheet, and ductility conversion into wires. So the D block element can be used in the formation of sheets. They can be used in the wires. In home appliances, you can see you are using the copper wire, the silver wire. You are using one. So then, due to their ductility nature, okay. So D block elements are both malleable and the ductile. So they are good conductor also. They are good conductor because they are metal, so they are good conductor also. So these about the properties of the D block elements. So thank you. That all about the characteristics of D block elements. So keep on watching in my next videos also. In the next lecture, we are discuss about the F block elements, characteristic of the F block elements. So thanks. for keeping patience and listening me so carefully. Thank you.